So maybe we should start now. Zuowei, is it okay?
Yeah.
Yeah. Good day, everyone. Welcome to the OneWorld seminar series on imaging and inverse problem. Before we start, I would like to make a short announcement. This OneWorld seminar series will be moving to Siam under the activity groups on imaging science. The web page will be moved to Siam, and then the weekly announcement will be sent by Siam. If you have already registered to this series, your name will be moved automatically to the Siam mailing list. We are doing the transition now, so it may take a few weeks to do this. Please stay tuned, and we will let you know once we have done the moving. And also, if you have any question about the talk, you can either post it in the Q&A box, or you use the raise hand button, and we will let you ask the speaker at the end of the talk. Now, let me introduce today's speakers. I'm very happy to have Zuowei Shen, my close friend, to give the talk today. Zuowei is the Tan Chin Tung Centennial Professor at the National University of Singapore. He received his PhD degree in 1991 from the University of Alberta. He first joined the National University of Singapore, the math department, in 1993, and then moving up the rank all through the years, first as a department head, then the Dean of Science, and just recently, he is now the Vice Provost of the university. Shen is known for his work on approximation theory, wavelet theory, and image processing. He was an invited speaker at the International Congress of Mathematicians in 2010, and an invited speaker at the 8th International Congress on Industrial and Applied Mathematics in 2015. Today, he will talk about image restoration and beyond. Let's, well, Zuowei, you have the floor.
Thank you, Raymond, for the nice introduction. Good day, everybody. And I would like thank you for all of you come to my talk. I also would like to thank organizers organizing such a wonderful seminar series, and also I would like to thank them for the invitation. When Raymond asked me to give a talk, I had some difficulties to choose the topic. As some of you may know, my recent research focus is on the approximation theory of the deep neural network. On the other hand, I have been working on last over 20 years and almost close to 30 years on wavelet theory and its application in imaging science. And after think about the interest of the audience, I decided to choose this image restoration and imaging topic. Some of the results, maybe a few years old results, but I think through the talk, you will know, you can see a picture of my research before I get into this approximation theory of a deeper neural network. So I will start from a few examples of photograph image restorations. And those are real image examples. Then since all the method I used is based on the wavelet frames, so I will spend a little time on multi-resolution analysis-based wavelet frame, and in the second part of my talk. Then I'm going to move to the models and algorithms. Especially, I want to see how the data can be used to improve your models and algorithms. And in the last part of the talk, I will show you how those ideas developed in this imaging restorations based on the wavelets can be applied to the other applications. So let's start the first example. Every data, all the data has noise, have noises, and image data, image also always have noises. And the problem is that normally we don't know what kind of noise we have. It's not always like a Gaussian noise or Poisson noise. You don't know. Maybe it's a mixture of everything. It's real data. You always have a noise. You don't know what kind of noise. So in this example, we design a very simple model for removing noise without knowing what kind of noise it is. This WC is a wavelet transform. That is a L1 normal wavelet transform. That is the regularization term. This is the normal. This pursue the sparsity for using L1 norm. And here with the key here, we have for that term, we have a mixture with the L1 norm and L2 norm. So this fidelity term can model, depending your parameter you choose, can model the noise pretty well. So here is the example. This is a noise image. This is a recovered image. So you may not see big noise in the noisy image. If you go to the blue channel, you can see. Okay, this is in fact in the blue channel, it is pretty noisy, and this is the clean image. Next photography images is deblurring. In fact, it's blind deblurring. Okay, image can be blurred by all kind of reasons, and this image given here was blurred by a shaking camera. So this is the recovered image. You can zoom in. You can zoom in. See, this is a pretty blur in this original image. So we recovered this image with sharp edges. In fact, most of the image restoration, the key point is sharpening the edges. Otherwise, denoising can be very simple. You just need to take average, but locally, but average will blur your edges. So the key point of the image restoration is the sharpening the image edges. Next, it's almost like 10 years ago, we had this series of project on this blind deblurring, and at that time it was pretty good, and even some people approach us for this further development. So next example is how to recover under or overexposed exposure region in the image. So this is the image. Okay, it's in this region of the image which is overexposed, and while in the other region it is underexposed. Okay, this is the recovery image, which is with a balanced exposure. So we can look at the zoom in, look at this overexposed region. That's the recovered region, and this is the underexposed region, and this is the recovered region. Here, next, I'm going to move on the MRI wavelets and the Gabor frames. This maybe is an old topic, but I like to went through a little bit, briefly went through. So here, the wavelet frame we use a redundant wavelet system. That's the frame, and is a MRI based. That means a multi-resolution analysis based wavelet frame. So the key ideas of multi-resolution start from the refinable function. A function phi is refinable if phi satisfies the following equation. This equation essentially says phi x can be written as a linear combination of the dilation of the phi and the shifts of the dilations. Okay, So there are many refinable functions. Okay, simple example for refinable functions are B-splines. I'm going to show you a few examples later. For refinable functions, there are two, not only function is important, also the mask is important. This mask H0, you call refinable mask. The refinement mask. Refinement mask also important in the sense, refinement mask first is uniquely decided by the refinable function phi. On the other hand, once you have the refinement mask, you can find phi also. That means the refinement of the function itself is also completely decided by the refinement mask. And later you can see this mask is basically used to do the computation. So function is for the analysis, computation is you use the mask. So this is with this refinable function, you can generate a multi-resolution analysis. And the wavelets also can be constructed by this phi. So how do we construct the wavelets? The constructed wavelets is you're using the wavelets also defined by the phi and its dilation and also translation of the dilation function. So you use the refinable function. So because we are using a redundant system, we kind of choose a set of the wavelets. This is passar 1, passar 2 until passar R. This set of wavelets, you want to define the wavelets given the refinable function, you just need to find HI, proper HI. What kind of HI you want to find? You want to find HI so that the passar is the dilation and translation from a wavelet system, which form a tight frame. So what's the condition for HI? This is a famous unitary extension principle. Unitary extension principle is, so given H0 is already given, that's given by the refinable function. So you go around to find HI. Around HI, you find I from 1 up to R. HI satisfies these equations. Then your wavelet system, X psi, is a tight frame. Okay, to set the notation, what are the X psi is? You give the wavelets, you make a dilation and a translation. Your dilation can be the 2 to the power n. N can run to the older integer, and your alpha is the older integer also. It's a translation, integer translation. This is the phi. Each wavelet will make a dilation and translation. You put all the dilation and translation together, you form a system. This system called the wavelet system. The wavelet system is tight frame if this identity holds. Okay, this identity, what does this identity hold means? That essentially tells you if you use wavelet system to sample your function, then it can be recovered by your sample completely with this data and with your wavelet system. This is a over 20 years old result. It was done it was published in the 1997 in my paper with Amos Ron. Later we generalize to a more general case. Okay, here's the example. So this is nice thing about the tight frame. You can use the B-spline to construct tight frame, compactly supported B-spline tight frame. This is our refinable function phi. It's piecewise linear. At 0 equal to 1, into the minus 1 equal to 0, and the 1 equal to 0. That's the piecewise linear spline, which is refinable. And you can generate 2 wavelets. These 2 wavelets, the dilation and translation all together, you will form the tight frame in L2. So another, the next example is the cubic spline, cubic B-spline. Then this you can generate 4 wavelets. That's the dilation and the translation from the tight frame. Here I like to note that you see, this H0 is the refinable mask. This is a very good mask. You can see it's a very good average. And H1, H2 also very good. Why? Later we are going to see why it's good, because This H0 and H2 is a standard difference operator. H2 is the first order difference operator. H1 is the second order difference operator. Same and the cubic, you have a standard difference operator from first order until the fourth order of a difference operator. Okay. Then the masks are important. As I always tell you, the masks are used for the computation. And all the wavelet masks are high pass filter. If you look at the filter, and all the refined mask is a lower pass filter. Okay. Why it's good? Because for the imaging that you give it, you can understand the image as your F sampled at the resolution N. Okay, this is the kind of, then when you do the computation, your wavelet transform, discrete transform is just for one level decomposition is just a convolution. Okay, it's very easy to compute. It's a convolution. Okay. The W is a we denote W as a wavelet transform. Here, especially is a discrete wavelet transform. So, as I said, when you do this computation, you only use this filter to do the discrete wavelet transform. So use the W as a discrete wavelet transform. The W, if you for the 1D case, you can view that this convolution matrix. This matrix is a rectangular matrix. Okay, it's a your low can consider the frame. So this is a very tall and thin matrix. If you use the redundant system, but this matrix has a property. This operator has a property. W and W transpose are equal to identity, and so this is your decomposition is the transform, and your reconstruction is the inverse transform. Inverse transform. So WTW become identity. If you flick the order, because it's a redundant system, it's become a projection, no more identity. Okay. So also, as I said, your system W, you can decompose the W as a consider as a system. Your loads as your tight frame system. You have two components. All the loads generated by the high pass filters, the wavelet masks. They're the high pass filters, and this high pass filter and when will catch the future, local features, especially singularity and edges of the image. And your lower pass filter is taking average. You catch the global pattern and also smooth information, smooth part of the image. The global pattern, in some sense, in many times, in most cases, it is more or less like the local information in the frequency domain. So you can see this is a typical piecewise constant imaging, and you pass the lower pass filter, you catch almost all the smooth and high pass filter, they catch the edges. That's why wavelets is good. Wavelet for image reconstruction, because image reconstruction is recover the edge. So in some sense, you recover to the image restoration. Essentially, you are trying to restore wavelet coefficients. Okay, wavelet coefficients reflects the edges. If you know the development of the wavelets, before wavelets become hot, they already have a wavelet frame become hot. It's already have a Gabor frame. Gabor frame is a system. If you forget about the G, this is just a Fourier basis. But Fourier basis has a problem that have a very bad time localization. So therefore, people think about people get the window. Okay, you get a window. This is the G. G can be a compactly supported or very fast decay function like a Gaussian. So then you have a window. Then you will shift the window. You get a system. This system form the frames in L2 function space. Of course, you digitize the system. You get Gabor filters. Okay, Gabor filter. Of course, it's a complex. The advantage for the Gabor filter, they have a very good time orientation. Oh, no, very good directional orientation. Okay, so that's the good directional frame. Okay, so you can see if you have an image which have a strong orientational preference, this using this kind of tight frame, it will perform better. That is true. We trust these three images over them at a very strong directional orientation. Then you can see for the denoise, this Gabor system perform best. But why people give up the Gabor system and move on the wavelets? Well, let's go back to here. People first complain your window is one size. You want to scale, window can be scalable. Then that's the one. And for the continuous wavelet is the frame Gabor frame system. For the digital filter system, for the Gabor system, you want to choose this good directional orientation. You need to do multi-level kind of decomposition. The multi-level decomposition is hard to justify if you don't have a built-in kind of multi-resolution analysis. So that's why people move from a Gabor frame to the web frame. That was a 30 years old story. However, it was a surprise to me. For a long time, people don't realize Gabor frame itself can generate multi-resolution wavelet frame. Gabor filter can generate multi-resolution analysis filters. That was surprising. This is not an old result. This is a new result, and it was just published in this couple of years. It has been appeared. So why? Okay, first of all, this result is supplied. First of all, you discover the result is already supplied, because for over 30 or 50 years, nobody, wavelet it become hotter in the last 30 years, but nobody even conjectures that the Gabor filter can form a MRA wavelet system. Nobody even conjectured. Okay, if you look at these two papers, we not only conjecture, we prove that it is. The proof is not so hard. Why the proof is not so hard? Because we based on our duality analysis foundation. But the duality analysis foundation, we first built up with Amos Long over 20 years ago. The first paper over 25 years ago. The first paper we published in 1995. But only recently, this duality principle or duality analysis we generalize to a more general setting suitable for any kind of wavelet frame system. This duality principle, this generalization makes this proof simple. So it's simple because we based on the heavy machinery. The heavy machinery take a long time to build up. And in fact, when Amos and I, we did this duality analysis, we use that to develop the unitary extension principle I stated before. For wavelet, we also have a duality principle for the Gabor frame in the early days. Okay, now we're back to the what kind of really you want to have a good system which either to approximate or represent image. What kind of system is good? Okay, look at wavelets. Wavelets is good because you have the system have a two subsystem. One is WH, one is WL. What WH is? WH essentially is the wavelet filters, and this catches local singularity. And WL catches global singularity, global pattern, and smooth part of the image. But this tool is very good for the multiple image restoration. But if you go further, you want to do the image classification or other things, you may need more. you also need to some subsystem maybe can catch global structure. That may not be smooth. That can be smooth, may not be smooth. And then at the end, you still need to catch some random feature. So this third part, I don't think wavelet really have this ability. But recently, I'm interested in the deep learning. You look at the neural network. Okay, neural network. If you look at this neural network image classification, neural network they also generate a system. This system is huge. It's much more redundant than wavelets frame. Those systems does catch some of the global structure. Okay. And because this is a much more powerful, much more bigger system, it's not only using linear combination, it's using the composition of the function. That makes it more powerful. So anyway, for your good system, you need a W to be redundant. So we have to give up those linear independencies, the autonomous concept. We have to go for the tight frame or redundant system. Okay. All the neural network, the systems, all the systems generated by the neural network are redundant. Okay. Also, these are all more complex. It's because of decomposition. That's lead me to the area. Okay. Next, we talk about the models and algorithm. Okay. Maybe my time is short. Okay. Let me run a little bit further, faster. So for image restoration, the typical one is you have the data G, but you are not happy with the G. You want to get the F. Okay, the F is generated, G is generated by the F pass through some operator, and they also have noise. Okay, with A is the identity here, then it's become a simple denoise problem. But when A is a blurring operator, you are deblurring. When you don't know A, then it's a blind deblurring. Okay. So what do people normally do? People normally have the problem, either deblurring or whatever the problem we have, the real life problem. First we try to find a model. Okay. To find the model, then based on the model, people normally develop algorithms. Then the algorithm lead to solutions. Okay. Now you have data. Data, now, so for many of our problems, sometimes you have many data available. So what the data can give to us? The data may either through learning or through other way, data may help you to improve the model. Okay, normally the model, you look at the, doesn't matter physical model or whatever many of the model we use, it's normally catch global pattern and a smooth component of your underlying solution. And the data hope also can give you local features. The local feature you want to catch, normally you have to catch through improved algorithms. It's pretty much true in many times. And of course, your data, you need the data also you can use the data to update and check whether you really achieve what you achieve. So many of the mathematicians are happy to do, you have a model, you develop an algorithm, you find the solutions. And the many of analysis we do is analysis of how much this solution close to the model solution. That's the main of analysis we are doing. But think about that. I always ask myself a question is, in fact, I don't care whether my solution close to model solution or not. What I care is whether my solution close to original solution of the problem. That's we should care. Okay, if you only care for the model solution, in some sense you ignore the problem solution, the arrow between the model and the problem. Okay, think about that. Can we do this way? Instead, we do that. We have a problem, real problem in our mind. Can we just develop our algorithm from our problem? Then can we analyze, and then you apply your algorithm to find a solution. Then your solution can we give the analysis how these solutions close to the original problems. That's the question. So then the people will challenge you. Where is your model? Okay, many people do that. You have a model. You use a model to develop algorithms and do the analysis. But on the other hand, sometimes you have an algorithm. Algorithm itself will lead to some, will converge to something. Something maybe lead you to some model. Okay, it's not necessary. You must have a model first. So now you can have a developer algorithm can test. Sometimes the algorithm itself will lead you, give you some, at least give you some motivation. What kind of model is the proper model? Also, you have a data. So data maybe can improve your algorithm. Also, so this sounds like it's different from what many people think, but in fact, many times we do this way. We not necessarily have a model first. Okay, let me give you an example and show you how my understanding lead to this kind of thinking. Okay, for last 30 years, okay, at least 10 years ago, find a sparse solution of equation is a hot topic. It's a hot topic because it's imaging, processing, also because of compressed sensing. 10 years ago, this time, compressed sensing is a hot topic. The key for the compressed sensing is to find a sparse solution of a certain equation. Okay, but this is the problem. Problem is to find a solution find a sparse solution for your equation. But many people focus on L1, L0 minimization. L0, L1 minimization is not, say, find a sparse solution. It's the model to find a sparse solution in some sense. Okay. So let's look at if you think about it, you want to find a sparse solution instead of think about the L1, L0 minimization, you will look at the different. Okay. Now you want to solve the equation AF equal to G. In fact, A is linear or non-linear is not important. Just you have some equation F equal to G. You want to find a solution. But what do you know? You only know that F has a good sparse approximation under some transformation. Okay, W. Okay, W can be linear and non-linear. But here the setting is not important. Okay, that's what it is. So the most naive way, what do you do? First of all, you find an approximate solution from this equation. Okay, you have to have a way to find it. Say A is linear, you have a many way to find this approximate solution of F. If I'm many way, okay, at least you can use this square to find one. So what's the problem for this solution? This solution, you maybe have a better numerical algorithm. You can get a better, already fairly accurate solution. What's the problem? Maybe the solution is not sparse under your transform domain. So what I do, very simple. I go to transform domain. I do the thresholding. I throw out a small coefficient. Then it becomes sparse. This is very good for image because the image we know if you use W as a wavelet transform, you throw out the small coefficients. You will sharp the edge. That's what your purpose. Your purpose is recover the edge. Then it transform back. That's all. Then, of course, you also cut the small coefficient. You may introduce some error. You do update the residues. You do iterate. Okay. So that's the key point here. Is not the L1 minimization, not the L0 minimization. Key point here is apply threshold in the domain where your solution has a sparsity. Okay, your thresholding, you have two kinds of thresholding. One is the soft thresholding, one is the hard thresholding. Hard thresholding just cut off, soft thresholding just shrink. Okay, this is what I did. This is the first project I did. This is super resolution image reconstruction. This super resolution image reconstruction you have a lower resolution. Maybe you have a several pieces. You want to recover the high resolution. This is the first paper I done on the imaging, and the first paper I applied wavelets on the to the image restoration. And this paper, our algorithm is this algorithm. Okay, this is exactly this algorithm. And I would like to use this opportunity to thank Raymond. He introduced me to this area and introduced me to this problem. We work together. This is the first paper. This, by the way, this is Chang Shen is not a typo. This the first Chang is Raymond Chang. Second Chang is Tony Chang. This Shen is not me. It's Li Xin Shen. So that time it was we did it 20 years ago. Okay, we developed iterative thresholding algorithm. It was not that popular there. People even don't believe it. It works. So it took us some time to get a paper to even get accepted. And the first question people will challenge you is that, okay, you are good, you have this algorithm. Okay, you do the iteration. Whether it converge or not. That's the first question people will ask. In fact, it does converge, but it took us some time. Okay, let's look at the simplest case. When A is identity, that becomes a denoising case. A becomes an identity, it converges. It converges what? Just one iteration converge. One iteration, you already converge to the minimizer of this thing. Okay? This is the L1 norm of your wavelet coefficient. And this one, I will talk a little about. This one is because you are redundant system. Each function, you have a many way to represent by your system. But you have a canonical system that which have a minimal L2 norm. This stays your system, your coefficient distant of your coefficient with canonical coefficient. Okay, this is what is the panel line. Okay, if you use an orthonormal system, this term automatically becomes 0. That is normally what people do. Okay, if you use orthonormal system, that's what it is. And for if you use the hard thresholding, it also converge to the L0 norm. Okay, here it becomes L0 norm. So it's a converged when A is identity. But when A is not identity, it's also converged, but it took us some time. Okay, it's also converged. And in fact, beta equals 0, people call synthesis-based approach. Okay, beta equal to between 0 and infinity, this is a balance. I call it balance. That's our approach because it's a balance between synthesis and analysis-based approach. Analysis-based approach, basically you take a beta equal to infinity. Okay. People always ask which one is better. You want for more regularity, more smooth, it's analysis-based. For if you want to have a more sparsity, it's a synthesis-based. And that if you want to balance between that, you choose your proper beta. Okay. In fact, it's converged even for the hard thresholding. Okay. It's also for the soft thresholding, we have lots of papers. Okay. Look at here. Here we don't have a model before. We have an algorithm. Algorithm lead to this converge to the minimizer of this cost function. That's can be your model. That's in fact is what people use. Or only different people use W. This is a non-redundant system. It's like an orthonormal basis or basis. This term becomes 0. So that's why normally people use that. But if you use a redundant system, this system doesn't matter you do, always there. This is our model. So the model is from algorithm. We have it took us some time to finally realize this algorithm not only work, it also converges. Okay, this L0 converges is recently, but there are many other papers we have done. Okay, this also comes to the next problem. Next problem is about matrix completion. So matrix completion is very simple. You have a matrix which has a low rank, Then if you only have a few entries, can you complete the matrix? Completely reconstruct the matrix? Yes, that's this theory work. They're done by Candace and his collaborators. And but look at that. If you look at what is the issue? If you have a matrix which is a low rank, that means what? Low rank means you have a sparsity in a single value domain. If you have a sparsity in the single value domain, then you want to use our 3 steps. You have to do what? My key point is you have to do the thresholding in single value domain. So that's the single value thresholding algorithm. That's the same as my 3 steps because it's simple. They're written in the 2 equations. This is you do the single value decomposition, you do the thresholding, and you reconstruct back. Okay. This is very good. This has become a very popular algorithm, and this lower rank matrix we use this result and to do many of the video reconstruction and segmentation and analysis. But I don't have time to talk about that. Well, while I'm very successful in the wavelet approach for the image restoration, then I was so excited. I gave a talk everywhere, and people always question me. The first question people normally ask is, how do you compare with the PDE approach? And it's easy to make a comparison because you can have a numerical simulation, you can have a results, you can show people the image. But the deep question is, mathematically, what's the connection between the wavelet frame approach and the PDE approach? So this leads to us a big project which have 4, I think, a very long paper, each of them about 50 pages. First paper, we make the connection with the wavelets and the total variation. Second paper, we make the connection between our wavelet approach with the evolution of the PDE's nonlinear evolution PDE approach. And the third one, we make the connection between the non-wavelet approach with this piecewise smooth function kind of approach. This is the Mumford-Shard approach in the special case of this. And the last, we also make the connection with the general variational method. Okay, this 4 paper, because we have a mathematically prove how do they connect. It's very technical and it's hard to say, to give a detail for this talk. But the key point is very simple. Key point, no matter which PDE approach you take, we can understand in some sense, you go to the wavelet transform domain, you make a map to the wavelet coefficient. Different approach of the PDE method, they make a different map. For example, total variation of the TV method, essentially you go to wavelet domain, apply the soft thresholding. That's the lead to the TV method. The nonlinear evolution for PDE, you go to the wavelet domain, you do a map of the wavelet coefficient. People normally call shrinkage. Different PDE you use essentially define a different kind of shrinkage. Okay, I gave you the idea, some idea for one of the papers. This is the typical model. If you take the D, the set of differential operators, if you take a gradient, that's the TV model. Okay, so this is our wavelet approach at the resolution N. Okay, so if you have a multi-resolution, you can this discrete, you can become the function case. That's why you need a function. You can help you analyze. You can reformulate in the function form. That's then you can consider. This is the 2 equivalent problem. We first can prove this ENF pointwise converge to this, and also gamma converges. As a result, you can see your any approximation solution, sequence of approximation solution for this problem, that satisfies this inequality. And any cluster point of that is an approximation of this original TV model. Okay. So this is Now, okay. So next, I give you my time is limited. I try to give you some a few examples how those ideas can use for the other things. First of all, our approach is basically sparse-based approach. You want to minimize that, and our experience says if your W under your transformation is good in the sense your underlying solution have a better sparse approximation for the underlying solution, you have a better result. So this leads to us to consider, can we data-driven to get the W instead of giving a fixed wavelet transform? That's what we do. Okay, we try to minimize not only for coefficient, also we try to choose D. But this okay, this minimization problem is equivalent to this problem, and solving this equation is simple because if you fix W, that's the hard thresholding, and if you fix C, this is solve this SVD problem, but it's only R by R. R is number of filter you use. Okay, so this is the very simple to use. Nowadays, people talking about the convolutional sparse coding, but convolutional sparse coding essentially is this approach. This is already done. We did it in the our first paper was published in the, I think 6 or 7 years ago. Okay, this for the denoising is in fact is not a supervised learning. We learn the system, but we can't see. At that time we have another only this data-driven kind of denoising using KSVD. But our approach is much faster, and we can prove this algorithm converges. Okay, so this also leads to this classification. So you basically use this system. You can using data to learn W, also learn your G here. Once you learn, this is your decoding, encoding, and then your decoding is you given an image. This is your W. You have this transform, and then you have this to lead to the classifier. Okay, so people will say now you have a deep learning. You kind of have a much higher accuracy for the classification, but a deep learning, you use a huge label set data. Okay, you have a huge labeled data. So, but for this, you can use a smaller set. Okay, so this will compare with the SVD. This method is not only accuracy is better. Our method first of all converges. Okay, this algorithm converges. We can prove, we already proved, and also we have a mathematical analysis for the accuracy. This is not all the other algorithms, even deep learning, you don't have this kind of theory. The theory tells us basically say, in short, say your accuracy, when your label data is big enough, you can mathematically prove you have your accuracy is close to 100% with high probability. Okay. Next, okay, because our connection between the PDE model and wavelet, so we can we can combine these two things. This do the surface fitting. So you see, we combine this wavelet method with the level set method. Level set method is very good to give the shape of the 3D surface reconstruction, the shape of the surface. But wavelet catch all the details, all the singularity. So to combine these together, I think we get a very good reconstruction. Also for the surface denoising, we can keep the small feature over the surface. And another example is the face retrieval. Face retrieval, this is the 4 standard image people normally use. And this is the faceless one. This is a faceless with noise. You almost cannot see much. And we can use our method to reconstruct. Okay, it all depends. Everybody can reconstruct. All depends on how many masks you will use. If you only using one mask, that means one set of data. Most of the available algorithm, that's what they reconstruct. But that our algorithm can reconstruct quite good. Okay, if you have 2 masks, even better. Okay, there's other argument you still cannot get much. Other argument normally you need 4 and more. And if you have a noise, we also works very well. Okay, last one is also it's interesting. You essentially you have a lights. Lights always pass through some system. Then you can collect the data. Okay, somehow what are the this is the collaboration with MIT as engineering faculty. So this is what you need. Essentially, is you need to how do I know the original density of the lights instead of only know what is past data from this you measure the data to predict the original really lights without past data. Then you can after that you can use so simulate the other system numerically. You can pass other system using this to pass that and see what the lights should be. Okay, that's basically our results. Okay, this is I think the paper. And I have a few survey papers, and I think touch many things. And in fact, I read recently a paper, survey paper in Chinese. That's the first paper I'm written in Chinese. So if I'm sure there in audience there are many people understand Chinese. You can read this paper also. Thank you very much.
Thank you, Zuowei. So we have one question in the Q&A. Maybe I ask you directly.
Okay.
What is the difference between model and algorithm?
Model. Okay.
Yeah.
Look at model is, for example, let's say compressed sensing. You want to find a sparse solution. People use the normal model is L1 or L0 minimization. That's your model. Your algorithm is to find minimizer. That's what people do. That's the model and algorithm is different. Model is a equation. The algorithm is to find the solution for the equation.
Okay.
Right. So yeah, I know that some engineering literature, they're mixture with the two. Okay, model is the equation to describe your original problem. But the equation, like your PDE is a model for many physics problem. But PDE, your solution is through algorithm to find the solution for PDE to get the solution for original problem. Right?
Okay.
That's the difference.
Okay.
Yeah.
So are there any other questions from the audience? Actually, I have one question. You mentioned it very interesting result about the Gabor frame. So now you proved that it's MRI wavelet frame, right?
Yeah.
So if I want to use it, so how do I know how do I control the approximation accuracy?
Oh, then you have a multi-resolution. You all the available tool can use. Because now you have using these other filter, then you the filter, you generate the underlying refinement function. You also have a weird function. Then all the web literature about approximation and also nonlinear approximation can be used.
So then I presume it's controlled by the G function, right? That you mentioned, right? So then somehow the G function should have some property. Am I correct?
Yeah. The function G condition is the minimum. There's not much condition. Then you later at the end where you use the G, you get the filters. Once you have the filters, you just have we need to satisfy certain property to make these filter become a MRI wavelet. Once you have an MRI wavelet, it all depends on your refinement function property to decide how good the approximation is.
Okay, I see. Okay. Okay, any other questions? Actually, Lixin is here, Lixin Shen, so the other author in the paper.
Oh, yeah.
He's in the audience, yeah.
Yeah,
so any other, sorry.
This paper is really changed my research direction.
Okay, any other questions or comments? Okay, I don't. Yeah, there seem to be no other questions. Okay. So then let us thank Zuowei for this very interesting and very informative talks about this all this development using this time frame and for the different applications. Yeah, thank you very much, Zuowei.
Thank you everybody.
Okay, bye bye.
Bye bye.